In the infinite reaches of space, there exists a realm untouched by time, an abyss where light dares not enter. It is a place beyond the understanding of science, beyond the imagination of humankind. Welcome to the Abyssal Universe, a hidden dimension lost in the dark. In this place, no star shines for long. The very fabric of reality bends and twists as if pulled by an unseen force. What you are about to witness is not a legend. It is a truth far more terrifying than anything we have known. At the edge of the known universe lies a boundary, an invisible line between what we can see and the vast unknown. Here, the stars themselves seem to wither and die, fading into the endless void. No one knows what lies beyond this line, but they call it the dark edge. Many have tried to explore this edge, but all attempts have failed. Probes disappear, communication is lost, and even light itself cannot escape its grasp. Some say that beyond this edge lies a different universe altogether, a place where time and space twist into something unrecognizable. It is a realm where the very laws of physics break down, a cosmic abyss that swallows everything in its path. What could possibly exist in such a place? At the heart of the Abyssal Universe lies the singularity of shadows. This is no ordinary black hole. It is a force so powerful that entire galaxies fall victim to its hunger. The singularity devours everything: light, matter, even time itself. But what makes it truly terrifying is what lies beyond its event horizon. Some believe it is not just a destructive force, but a portal, a gateway to something far more dangerous. If anyone were to pass through the singularity of shadows, what would they find on the other side? Is it the birthplace of the universe or its ultimate end? The whispering void, a place where sound has no meaning, and yet there are voices. Faint whispers echo across the void, carried on cosmic winds that do not exist. These whispers are not random. Some believe they are the voices of lost civilizations, consumed by the abyss. Others think they are messages, warnings from the darkness itself. Whatever they are always there, lurking just beyond the edge of perception. They speak of things we cannot comprehend, and of a fate that awaits us all. In this universe, not even the stars are safe. The dying stars, as they are called, mark the boundary between life and total oblivion. One by one, they are snuffed out, their light extinguished forever. Some theorize that the stars themselves are being consumed by the abyss, their energy drained by an ancient force older than the universe. Others believe the stars are simply giving up, surrendering to the endless dark. When the last star dies, what will remain? But even in the deepest reaches of the abyss, something watches. The cosmic eye, as it is known, appears only for those who wander too far into the dark. It is an ancient, unfathomable entity, silent, still, and always observing. Some say it is a god. Others believe it to be the final guardian of the abyss. Whatever it is always there, waiting for those foolish enough to seek its gaze. And in the end, the Abyssal Universe is not just a place, it is a presence, a living, breathing darkness that watches, waits, and eventually consumes everything. There was a time, if we can even call it that, when nothing existed. No stars, no galaxies, no space, not even time itself. And yet in this nothingness, something extraordinary happened. The universe as we know it began with a moment so powerful, so mysterious, that it defies the very fabric of reality. In an instant, the universe was born in a violent explosion of energy and light. The Big Bang. This was the beginning of everything, a cosmic event that set the stage for all that exists today. Nearly 14 billion years ago, the universe was nothing more than a singularity, a point of infinite density and unimaginable heat. In less than a fraction of a second, this point expanded faster than the speed of light, creating space and time in what we now call the Big Bang. The Big Bang wasn't an explosion in space, it was the expansion of space itself. From this tiny point, the universe expanded, and within just 10 Mars or 43 seconds, the universe grew from something smaller than an atom to a size larger than a galaxy. In the beginning, the universe was a hot, dense soup of energy, far too chaotic for anything like stars or planets to exist. This was the Planck epoch, a time when the laws of physics as we know them didn't apply. It was a moment in cosmic history that remains one of the greatest mysteries of science. But in this chaos, something remarkable happened, a moment that would shape the future of the universe. Just a trillionth of a second after the Big Bang, the universe entered a phase of rapid inflation. Imagine space itself stretching faster than light, flinging everything outward into the vast emptiness. The inflationary epoch. During this phase, the universe expanded exponentially, doubling in size over and over again in less than a blink of an eye. This expansion was critical. It smoothed out the chaos, allowing matter to spread across the universe in a uniform way. Without inflation, the universe might have collapsed back in on itself, or formed irregularly, preventing stars and galaxies from ever coming into being. As the universe expanded and cooled, it entered its next phase, an age where the building blocks of matter began to take shape. The universe was now a quark-gluon plasma, a thick, energetic soup of the smallest known particles. Quarks, the tiny particles that make up protons and neutrons, and gluons, the force that holds them together, filled the early universe. Quarks are the fundamental particles that make up all matter. In these early moments, they were free, swirling in a chaotic dance with no structure or form. But as the universe cooled further, these quarks began to bind together, forming protons and neutrons, the very particles that would later form atoms, stars, and galaxies. This was the first step toward a structured universe. In the minutes following the Big Bang, the universe underwent another vital transformation. As temperatures dropped to about 1 billion degrees, protons and neutrons began to fuse together in a process called nucleosynthesis. This was the birth of the first elements, hydrogen and helium. Hydrogen, the simplest element, is the most abundant in the universe. Helium, created through nuclear fusion, makes up much of the rest. Together, these two elements account for about 98% of all matter in the cosmos. From this point onward, hydrogen and helium would become the fuel for the first stars, the engines of creation that would one day light up the universe. As the universe continued to expand and cool, it reached a critical moment. Around 380,000 years after the Big Bang, the universe became transparent. For the first time, light was able to travel freely across space. This light is what we now know as the cosmic microwave background, the oldest light in the universe. The cosmic microwave background, CMB, is a faint glow that fills the entire universe. It's a remnant of the Big Bang, a snapshot of the universe when it was just 380,000 years old. The CMB tells the story of the early universe, its temperature, its structure, and its expansion. This light has traveled for billions of years, and even today, we can detect it as a faint, glowing remnant of the beginning of everything. After the cosmic microwave background was released, the universe entered a period of darkness. No stars had yet formed, and space was filled with vast clouds of hydrogen and helium. These were the dark ages of the universe, a time where the cosmos was waiting for its next great transformation. The dark ages lasted for hundreds of millions of years, with no visible light or stars. During this time, gravity was slowly pulling gas together, preparing for the birth of the first stars. And then, after millions of years of darkness, the universe ignited. Gravity pulled clouds of gas together, compressing them until nuclear fusion began. The first stars were born, lighting up the cosmos and bringing the universe out of its dark ages. These first stars, known as population 3 stars, were massive and burned incredibly hot. They lived short lives, dying in violent supernovae that spread heavier elements across space. The birth of the first stars was only the beginning of the universe's grand design. As the early universe continued to evolve, something incredible happened. Individual stars began to gather, forming the first galaxies. Together, these galaxies would create a vast, interconnected structure that spans across the universe, shaping the cosmos as we know it today. In the early universe, gravity continued to play its role as the architect of creation. Clouds of gas and dust, rich with hydrogen and helium, began to collapse under their own gravity, forming dense clusters of stars. These clusters of stars weren't isolated. They were drawn together by gravity, forming the very first galaxies. Galaxies began to form around 200 million years after the Big Bang, during a period known as the Cosmic Dawn. These galaxies were much smaller than those we see today, but were the first true structures in the universe. These early galaxies were smaller and more irregular, filled with young, massive stars that burned brightly and lived short, explosive lives. Over time, these galaxies merged and grew, evolving into the stunning spiral and elliptical shapes we see today. As the universe aged, galaxies began to take on a variety of shapes and forms. Some became stunning spirals with elegant arms winding around a central bulge of stars. Others became elliptical, more spherical or football-shaped clusters of stars without the dramatic arms of spiral galaxies. Then, there are the irregular galaxies, chaotic and undefined in shape, often the result of galactic collisions and mergers. Our own galaxy, the Milky Way, is a spiral galaxy with a supermassive black hole at its center, surrounded by a disk of stars, gas, and dust that forms its iconic arms. At the heart of the Milky Way lies Sagittarius A, a supermassive black hole with a mass millions of times greater than the Sun. It anchors our galaxy, holding it together as stars and gas orbit around it. Elliptical galaxies are some of the largest galaxies in the universe, containing hundreds of billions of stars. These galaxies have little gas and dust, meaning that star formation in them has mostly ceased. Galaxies are not scattered randomly across the universe. They are part of a much larger structure known as the cosmic web. This web is made up of filaments of dark matter, a mysterious substance that binds galaxies together, forming clusters and superclusters. These clusters are the building blocks of the universe's vast architecture. Dark matter makes up about 85% of the total mass of the universe, yet it cannot be seen or directly detected. Its presence is inferred through its gravitational effects, shaping the structure of galaxies and galaxy clusters. The cosmic web is a network of galaxies and dark matter stretching across the entire universe. Galaxies form along the filaments of this web, with vast empty spaces or voids between them. These structures are the scaffolding of the universe, holding everything together on the largest scales. The Virgo supercluster, where our own galaxy is located, is just one of millions of such superclusters in the universe. The largest structures we know of span over 1 billion light-years across, connecting countless galaxies. Galaxies are not static. They are constantly in motion, drifting through space and interacting with one another. Sometimes galaxies collide, merging into a single larger galaxy. While this might seem like a destructive process, it's also one of creation. When two galaxies collide, the individual stars within them rarely collide directly due to the vast distances between stars. However, the gravitational forces involved can create tidal distortions, pulling stars and gas into new positions. The collision of galaxies often triggers a burst of star formation as gas clouds are compressed. These collisions can result in the formation of entirely new galaxies, with some tacking on irregular shapes during the process. While the stars themselves remain largely unaffected, the gas clouds within galaxies are disturbed, creating new waves of star formation. Over millions of years, these merging galaxies will settle into a new, larger form. Even our own Milky Way is on a collision course. The Andromeda Galaxy, our nearest large galactic neighbor, is moving toward us at a speed of 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide, merging into a single massive galaxy. The Milky Way and Andromeda galaxies are part of the Local Group, a collection of more than 50 galaxies that includes the Triangulum Galaxy and several smaller dwarf galaxies. This collision won't be the end of either galaxy, but the beginning of something new. Over millions of years, the two galaxies will merge, forming a larger elliptical galaxy. But for any inhabitants living on planets in the Milky Way, the night sky will be dramatically changed. Galaxies evolve over billions of years. Young galaxies are filled with hot blue stars and glowing nebulae, places where new stars are still being born. Over time, as galaxies age, their star-forming regions slow down, and they begin to run out of the gas needed to create new stars. The color of a galaxy can tell us about its age. Blue galaxies are younger and more active, while older galaxies take on a redder hue as their stars age and die. As galaxies age, their stars die, becoming white dwarfs, neutron stars, or black holes. The galaxy itself becomes dimmer and quieter, no longer able to create new stars. The story of a star begins in the cold depths of space, within vast clouds of gas and dust known as nebulae. These regions, called stellar nurseries, are the birthplace of stars. Inside these clouds, gravity slowly takes over, pulling material together, causing the cloud to collapse. As the gas and dust compress, something extraordinary happens. The temperature and pressure at the core of the cloud rise to extreme levels, and a star is born. Stars are born when the temperature at the core of a collapsing gas cloud reaches about 15 million degrees Celsius, igniting nuclear fusion. This fusion process converts hydrogen into helium, releasing vast amounts of energy. This process, nuclear fusion, powers a star, allowing it to shine for millions or billions of years. The star's light marks the beginning of a life cycle that will eventually lead to either a quiet fade or a violent, explosive death. Young stars are often surrounded by leftover gas and dust, which can eventually form planets, moons, and other celestial bodies in the star's orbit. Not all stars are created equal. Some are small and faint, living quietly for trillions of years, while others are massive, burning fiercely and living fast but dying young. The size and mass of a star determine its entire life cycle, from how long it will burn to how it will eventually die. Small stars, known as red dwarfs, are the most common type of star in the universe. They burn their fuel slowly and can live for up to 1 trillion years, far longer than the current age of the universe. Larger stars, like blue giants, burn much hotter and faster. These stars live for only a few million years before they exhaust their fuel and face their dramatic fate. A star's color can tell us about its temperature and lifespan. Blue stars are the hottest and burn their fuel the quickest, while red stars burn cooler and can survive for far longer. Our own sun, a yellow dwarf, sits somewhere in between. It will live for about 10 billion years, and it is currently around halfway through its life. The sun, our closest star, is the engine of life on Earth. This medium-sized star has been burning for 4.6 billion years, and it has enough fuel to last for another 5 billion. Like all stars, the sun is powered by nuclear fusion, fusing hydrogen into helium at its core and releasing immense amounts of energy. The sun's surface temperature is around 5,500 degrees Celsius, while its core burns at over 15 million degrees Celsius. While the sun may seem calm from Earth, its surface is a violent, ever-changing landscape. Solar flares and sunspots are evidence of the sun's magnetic activity, and sometimes these solar storms can impact us on Earth, creating auroras and even disrupting communication satellites. Stars, like all things, must eventually die. As stars exhaust their supply of hydrogen, they begin to burn heavier elements, causing them to swell into red giants. For stars like our sun, this marks the beginning of the end. When stars like the sun run out of hydrogen, they start fusing helium into carbon, causing them to expand into red giants. Our sun will one day swell so large that it will engulf the inner planets, including Earth. In about 5 billion years, the sun will become a red giant, expanding so far that it will swallow Mercury, Venus, and possibly Earth itself. Eventually, it will shed its outer layers, leaving behind a dense core, a white dwarf. White dwarfs are the remnants of stars like our sun. They are incredibly dense and will slowly cool and fade over billions of years, eventually becoming black dwarfs. For stars much larger than the sun, death is far more dramatic. When a massive star runs out of fuel, it can no longer support itself against the force of gravity. In a fraction of a second, the core collapses, triggering one of the most powerful events in the universe: a supernova. A supernova is a stellar explosion that can outshine an entire galaxy for a short period of time. The explosion releases so much energy that it can create elements heavier than iron, such as gold and uranium. Supernovae are responsible for distributing heavy elements throughout the universe. These elements, created in the intense heat of the explosion, are the building blocks of planets, moons, and even life itself. The core left behind after a supernova depends on the mass of the star. If the star was massive enough, its core will collapse into a neutron star, a city-sized object with a mass greater than the sun. Some neutron stars become pulsars, rotating rapidly and emitting beams of radiation. Neutron stars are incredibly dense. Just a teaspoon of neutron star material would weigh billions of tons. Pulsars spin at incredible speeds, with some rotating hundreds of times per second. Their regular pulses of radiation make them some of the most accurate cosmic clocks in the universe. But for the most massive stars, the collapse continues until even light cannot escape. These stars leave behind black holes, regions of space where gravity is so intense that not even light can escape. These black holes represent the final chapter in the life of the most massive stars. The life and death of stars is a cycle that has shaped the universe for billions of years. From their birth in stellar nurseries to their death as white dwarfs, neutron stars, or black holes, stars are the engines of creation. They forge the elements that make up planets, moons, and even life itself. And those stars die, their legacy continues as new generations of stars and planets form from the remnants of their spectacular deaths. In the endless dance of creation and destruction, stars remind us of the universe's ability to renew itself, even in the face of cosmic chaos. There are places in the universe where even light cannot escape, where time and space are stretched to their limits and the laws of physics break down. These are black holes, the most mysterious and terrifying objects in the cosmos. Born from the collapse of massive stars, black holes are the final resting places of matter, energy, and even light. A black hole begins its life in death. When a massive star reaches the end of its life, it can no longer generate the energy needed to counteract the force of gravity. The core collapses in on itself, creating a point so dense, so compact, that it forms a region where gravity becomes overwhelming, a black hole. Black holes are formed from stars with at least 20 times the mass of our sun. When these stars collapse, they leave behind a singularity, an infinitely dense point surrounded by an event horizon. At the center of the black hole lies a singularity, a point of infinite density where the known laws of physics no longer apply. This singularity is surrounded by an event horizon, the point of no return. Once something crosses this boundary, there's no escaping the gravitational pull of the black hole. The event horizon is perhaps the most defining feature of a black hole. It marks the boundary beyond which nothing, no matter how fast, can escape, not even light. From the outside, the event horizon appears as a sphere of darkness, a region where light is bent and swallowed by gravity. The escape velocity at the event horizon is greater than the speed of light, which is why nothing can escape once it crosses this threshold. Beyond the event horizon, space and time are distorted beyond recognition. Time itself behaves differently near a black hole. The closer you get to the event horizon, the slower time flows, at least from the perspective of an outside observer. If you were to watch someone fall into a black hole, they would appear to freeze in time at the event horizon, their light stretched and red-shifted into oblivion. Not all black holes are the same. While many are formed from the collapse of individual stars, some black holes are far larger, millions or even billions of times the mass of the sun. These are the supermassive black holes, cosmic giants that lie at the centers of most galaxies, including our own Milky Way. Stellar black holes are formed from the collapse of massive stars and typically range from 3 to 10 times the mass of the sun. Supermassive black holes, on the other hand, can have masses millions to billions of times greater. Sagittarius A, the supermassive black hole at the center of the Milky Way, has a mass equivalent to 4 million suns. These massive black holes are thought to play a key role in the formation and evolution of galaxies, anchoring entire star systems in their immense gravitational pull. While black holes themselves are invisible, their presence is revealed by the matter they consume. As gas, dust, and even stars are pulled toward a black hole, they form an accretion disk, a swirling disk of superheated material spiraling into the abyss. The friction and pressure in the disk heat it to millions of degrees, causing it to glow brightly, often outshining entire galaxies. The intense heat of the accretion disk can produce X-rays and other forms of high-energy radiation, making black holes some of the brightest objects in the universe, despite their dark cores. Some black holes also produce relativistic jets, powerful streams of radiation and particles that shoot out from the poles of the black hole at nearly the speed of light. These jets can extend for thousands of light years into space. One of the most powerful events in the universe is the collision of two black holes. When two black holes orbit each other, they gradually lose energy through the emission of gravitational waves, spiraling closer and closer together. Eventually, they collide and merge, forming a single, larger black hole. The energy released in such mergers is so immense that it distorts space and time itself. In 2015, scientists detected gravitational waves for the first time, confirming a prediction made by Albert Einstein a century earlier. These waves were produced by the merger of two black holes more than 1 billion light-years away. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, like black holes. These waves travel across the universe, carrying information about their origin. At the heart of every black hole lies one of the greatest mysteries of modern science, the singularity. This is the point where all the mass of the black hole is concentrated and where gravity becomes so strong that space and time themselves collapse. It's a place where the known laws of physics break down. In a singularity, the density becomes infinite and time and space become distorted beyond recognition. Scientists still don't fully understand what happens at the singularity, as our current models of physics, including general relativity, cannot describe the conditions at this extreme point. Understanding the singularity could unlock deeper truths about the universe, about gravity, space-time, and even the nature of reality itself. But for now, it remains one of the greatest mysteries in astrophysics. One of the most puzzling questions about black holes is what happens to the information contained in the matter that falls into them. According to quantum mechanics, information can never be truly destroyed. But when something crosses the event horizon of a black hole, it seems to disappear forever, leading to a paradox. The information paradox arises from a conflict between quantum mechanics and general relativity. While quantum theory suggests that information can't be destroyed, black holes seem to erase it from the universe when they consume matter. Scientists are still debating whether black holes truly destroy information or if it is somehow preserved, possibly through mechanisms we don't yet understand. Solving the information paradox could provide critical insights into the relationship between quantum mechanics and gravity. Black holes are the ultimate enigma. They are the darkest, most destructive objects in the universe, and yet they are also gateways to the unknown, places where the rules of reality no longer apply. As we continue to explore the cosmos, black holes remain a source of wonder and mystery, challenging our understanding of space, time, and the fabric of the universe itself. The universe is full of wonders, stars, galaxies, and planets, all visible to us in the night sky. But what if we told you that everything we see, all the stars, all the galaxies, make up less than 5% of the universe? The rest of it, the overwhelming majority, is made of invisible, mysterious forces, dark matter and dark energy. In the 1930s, astronomers made a startling discovery. As they observed galaxies spinning in the cosmos, they expected to find that the stars at the edges of galaxies move slower than those near the center, as dictated by the visible mass of the galaxy. But to their surprise, the stars at the outer edges were moving just as fast as those near the center. This phenomenon was first noticed by Swiss astrophysicist Fritz Zwicky, who suggested that there must be some unseen mass providing the extra gravity needed to keep the galaxies together. The only explanation was that there had to be far more mass than what was visible, an unseen substance exerting gravitational pull. This invisible material became known as dark matter, a substance that makes up about 27% of the universe. Despite its name, dark matter isn't made up of anything we know. It doesn't emit light or energy, and it doesn't interact with electromagnetic forces like the matter we're familiar with. So what exactly is dark matter made of? The truth is, we don't know. Dark matter doesn't interact with regular matter except through gravity. It doesn't absorb, emit, or reflect light, which makes it impossible to detect directly. One of the leading theories suggests that dark matter might be made up of particles called WIMPs, weakly interacting massive particles, or even more exotic particles like axions, which have yet to be directly observed. Scientists have been searching for dark matter for decades. Experiments deep underground and in space have been designed to detect dark matter particles, but so far they remain elusive, hidden in the darkness. Even though we can't see dark matter, we can see its effects. Dark matter is essential to the formation of galaxies and galaxy clusters, creating a cosmic web that holds everything together. Without it, galaxies would fly apart, unable to stay intact under their own gravity. Dark matter provides the extra gravitational force needed to bind galaxies and galaxy clusters together. It is believed to surround galaxies in massive halos, forming the backbone of the cosmic web. In a sense, dark matter is the scaffolding of the universe. It shaped the structure of the cosmos after the Big Bang, and it continues to influence the movement and formation of galaxies today. We owe the very existence of galaxies, and perhaps life itself, to this invisible substance. While dark matter holds the universe together, something else is tearing it apart. In 1998, scientists made a shocking discovery. The universe isn't just expanding, it's expanding faster and faster. This discovery suggested that some mysterious force was driving the expansion of the universe, pushing galaxies farther apart. That force is what we now call dark energy. Dark energy makes up a staggering 68% of the universe, dwarfing both regular matter and dark matter. It is the dominant force shaping the future of the cosmos. Dark energy behaves like an anti-gravity force, counteracting the pull of gravity and accelerating the expansion of the universe. But what is it? Once again, we don't know. Dark energy is even more mysterious than dark matter. It's not made of particles like regular matter or dark matter. Instead, scientists think it might be a property of space itself, a kind of energy that's woven into the fabric of the universe. One of the leading theories is that dark energy is related to the cosmological constant, a term first introduced by Albert Einstein. It suggests that space itself has an inherent energy that drives the expansion of the universe. Einstein originally added the cosmological constant to his equations to explain a static universe, but after the discovery of the expanding universe, he called it his greatest blunder. However, with the discovery of dark energy, the cosmological constant may have been more insightful than he realized. Another possibility is that dark energy could be a new, undiscovered form of energy or a dynamic field that changes over time, affecting the rate of expansion differently in different eras of the universe. Dark energy doesn't just affect the present, it will shape the ultimate fate of the universe. If dark energy continues to dominate, the universe could face a slow, cold death known as the Big Freeze. In this scenario, galaxies will drift farther and farther apart until all the stars burn out, leaving nothing but black holes and a dark, empty cosmos. In the Big Freeze, the universe continues to expand forever, but at a faster and faster rate. Stars eventually run out of fuel, and no new stars can form. Over trillions of years, all sources of light and heat will fade away. But there's another, even more dramatic possibility. If dark energy's influence grows stronger over time, it could eventually tear the universe apart in a catastrophic event known as the Big Rip. In this scenario, the expansion becomes so extreme that not only galaxies but stars, planets, and even atoms are ripped apart. The Big Rip could occur if dark energy becomes more powerful with time. In the final moments, space-time itself would be torn apart, and the universe would end in a violent and chaotic dissolution. Despite the incredible impact dark matter and dark energy have on the universe, they remain some of the greatest mysteries in modern science. Around the world, scientists are working tirelessly to unlock their secrets, using advanced detectors, space observatories, and particle accelerators in the hopes of detecting these invisible forces. Experiments like the Large Hadron Collider and dark matter detectors deep underground are attempting to detect the elusive particles that might make up dark matter, while space telescopes like the Dark Energy Survey are mapping the universe's expansion to learn more about dark energy. The search for dark matter and dark energy could revolutionize our understanding of the universe, revealing new physics and possibly even new dimensions of reality. But for now, they remain the unseen forces shaping the fate of the cosmos. The universe we see is only a small fraction of what exists. Dark matter and dark energy are the invisible forces that bind galaxies together and drive the expansion of space. While they remain some of the greatest mysteries in modern science, their influence is undeniable. As we look to the future, solving these cosmic puzzles may hold the key to understanding the true nature of the universe and our place within it. For centuries, humans have gazed up at the night sky, wondering if we are alone in the universe. Are there other planets like Earth? Are there other forms of life hidden among the stars? Today, we know that our solar system is not unique. Beyond our sun, there are billions of stars, and orbiting them are planets, worlds that could hold the key to answering one of the greatest questions of all time. Are we alone in the universe? For most of human history, the idea of planets outside our solar system was the stuff of speculation and science fiction. But in 1992, everything changed. Astronomers made the first confirmed discovery of exoplanets, planets orbiting a star beyond our sun. These planets orbiting a pulsar were far from what we imagined. Then just 3 years later, a groundbreaking discovery was made, an exoplanet orbiting a sun-like star. In 1990, the exoplanet 51 Pegasi b was discovered orbiting a star similar to our sun, marking the first confirmation of an exoplanet in a solar system like our own. This discovery marked the beginning of a new era in astronomy. Since then, we have discovered thousands of exoplanets, worlds with diverse landscapes, temperatures, and conditions. Some are massive gas giants like Jupiter, while others are rocky, Earth-like planets that could potentially support life. But how do we find these distant worlds? Exoplanets are so far away that they can't be observed directly with most telescopes. Instead, astronomers rely on indirect methods to detect their presence. One of the most effective methods is the transit method, which detects the tiny dip in a star's brightness when a planet passes in front of it, blocking a small portion of its light. The transit method has been responsible for the discovery of the majority of known exoplanets. By observing the light curve of a star, astronomers can infer the presence of a planet and even estimate its size and orbit. Another technique is the radial velocity method, which detects the slight wobble of a star caused by the gravitational pull of an orbiting planet. This wobble shifts the star's light spectrum, allowing astronomers to calculate the planet's mass. The universe is full of a staggering variety of exoplanets. Some are gas giants larger than Jupiter, orbiting close to their stars in what are called hot Jupiters. Others are rocky, Earth-like planets, potential candidates for life. Then there are planets with conditions we can barely imagine, worlds made of ice, planets with molten surfaces, and even planets where it rains iron. Hot Jupiters are gas giants that orbit extremely close to their stars, completing an orbit in just a few days. These planets are blasted with intense radiation, making them some of the hottest known worlds in the universe. Super-Earths are rocky planets larger than Earth, but smaller than Neptune. Some of these worlds may have thick atmospheres, while others could be more like Earth, with oceans, mountains, and potentially habitable conditions. One of the key factors in the search for life is the habitable zone, the region around a star where temperatures are just right for liquid water to exist. It's often called the Goldilocks zone because it's not too hot, not too cold, but just right for life as we know it. The habitable zone depends on the size and temperature of the star. For small, cool stars, the habitable zone is much closer to the star, while for larger, hotter stars, it's farther out. Planets in the habitable zone have the potential to support liquid water on their surface, which is essential for life as we know it. But finding a planet in the habitable zone is just the first step. There are many other factors that determine whether a planet can actually support life. As we continue to discover more exoplanets, a few have stood out as potential candidates for life. One of the closest is Proxima b, a rocky planet orbiting Proxima Centauri, the closest star to our sun. Proxima b lies within the habitable zone of its star and is only 4.2 light-years away. Proxima b is about 1.3 times the mass of Earth and orbits its star every 11 days. However, its proximity to its star means it could be bombarded by intense radiation, making its habitability uncertain. Another fascinating system is TRAPPIST-1, a red dwarf star with 7 Earth-sized planets orbiting closely. 3 of these planets lie within the habitable zone and may have conditions suitable for liquid water. The TRAPPIST-1 system is located about 40 light-years away, and its planets are so close to each other that they would appear large in each other's skies, creating a potentially stunning view for any inhabitants. Then there's Kepler 422b, often called Earth's cousin. This planet orbits a sun-like star in the habitable zone and is about 60% larger than Earth. While we don't know much about its atmosphere, Kepler 422b remains one of the most Earth-like exoplanets discovered so far. Finding planets in the habitable zone is only part of the challenge. To determine whether a planet can support life, scientists look for certain biosignatures, chemical clues that could indicate the presence of living organisms. One of the most important signs is the presence of oxygen in a planet's atmosphere. Oxygen is highly reactive, so it wouldn't remain in an atmosphere for long without being replenished by life, such as photosynthetic organisms. Finding oxygen, along with other gases like methane, could be a strong indicator of life. The James Webb Space Telescope, launched in 2021, is one of the most advanced tools we have for studying exoplanet atmospheres. With its powerful instruments, it can analyze the light passing through a planet's atmosphere to detect the chemical composition, potentially revealing the building blocks of life. With billions of stars in our galaxy alone, and potentially trillions of planets, the odds of life existing elsewhere seem high. And yet, we've found no clear signs of life beyond Earth. This contradiction is known as the Fermi paradox. If life is common in the universe, why haven't we found it? The Fermi paradox is named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Despite the vast number of planets that could potentially harbor life, we have yet to detect any extraterrestrial civilizations. The search for life continues as we explore the farthest reaches of space and analyze the atmospheres of distant worlds. Whether we're alone in the universe remains one of the greatest unanswered questions of our time. But with each new discovery, we come one step closer to finding out. The universe is vast, and the search for new worlds is just beginning. With each discovery, we learn more about the incredible diversity of planets beyond our solar system. Somewhere out there, among the billions of stars, there may be a planet with oceans, mountains, and perhaps even life. As we continue to explore the cosmos, we look to the future with hope and curiosity, wondering what secrets these distant worlds hold. Since the moment of the Big Bang, the universe has been expanding. Galaxies are moving away from each other, carried by the expansion of space itself. But this expansion isn't slowing down, it's speeding up. The discovery of dark energy in the late 20th century revealed that the universe is not only expanding, but doing so at an accelerating rate. In 1998, scientists discovered that the expansion of the universe was accelerating, driven by an unknown force called dark energy. This mysterious energy makes up about 68% of the universe. If this expansion continues unchecked, the future of the universe could be one of endless growth, a future where galaxies drift so far apart that the night sky will go dark, and stars, planets, and even atoms might cease to exist as we know them. One possible fate of the universe is known as the Big Freeze. In this scenario, the universe continues expanding forever, but at an increasingly rapid pace. As galaxies move farther apart, fewer new stars are born, and the existing stars burn out, leaving cold, dead remnants behind. In the Big Freeze scenario, galaxies will become so distant from each other that their light will never reach their neighbors. Eventually, all star formation will stop, and the universe will grow cold and dark. Over trillions of years, the last stars will burn out, leaving behind only black holes, neutron stars, and white dwarfs. As the universe grows colder, all sources of light and heat will fade away, leaving a cold, dark, and empty cosmos. In the distant future, after the last stars have faded, the universe will enter what scientists call the black hole era. Black holes, the remnants of massive stars, will become the last dominant objects in the universe, consuming anything that strays too close. During the black hole era, black holes will slowly consume the remaining matter in the universe, including stars, gas, and even other black holes. Eventually, they will become the only significant structures left. As black holes continue to consume everything in their path, they will merge and grow larger. But even black holes cannot last forever. Over time, they will begin to slowly evaporate through a process known as Hawking radiation. In the 1970s, physicist Stephen Hawking proposed that black holes are not completely black. Over incredibly long periods of time, they emit tiny amounts of radiation, causing them to slowly lose mass. This process, known as Hawking radiation, means that even black holes will eventually disappear. Hawking radiation is a slow process. A black hole with the mass of the Sun would take about 10⁻⁻⁶7 years to evaporate completely. As black holes evaporate, they will release their energy into the cold, empty universe. Eventually, the last black hole will disappear, leaving behind a universe devoid of light, matter, and structure. After the black hole era comes the dark era, the final stage of the universe, where no light, no heat, and no structure remain. The universe will be an empty, dark void, filled only with faint particles drifting endlessly through space. In the dark era, the universe will have expanded to such a degree that any remaining particles will be so far apart that they can no longer interact. It will be a cold, lifeless, and static universe. The universe will have reached a state of maximum entropy, a state where no more energy can be used, no more work can be done, and no new structures can form. Time will continue, but nothing will ever change again. This is the ultimate end of the universe in the Big Freeze scenario. While the Big Freeze is one of the most widely accepted theories, it is not the only possible fate of the universe. Another possibility is the Big Crunch, a scenario in which the expansion of the universe eventually slows, stops, and reverses. In the Big Crunch, gravity would overcome the expansion of the universe, pulling galaxies, stars, and everything else back together. Over time, the universe would collapse in on itself, eventually returning to a singularity, similar to the one that existed before the Big Bang. If the universe were to experience the Big Crunch, all matter, space, and time would collapse into a singularity, potentially leading to a new Big Bang and the birth of a new universe. The cycle of creation and destruction could continue indefinitely. There is another more violent possibility for the end of the universe, the Big Rip. In this scenario, dark energy doesn't remain constant. It grows stronger over time. As dark energy accelerates the expansion of the universe, it eventually tears apart galaxies, stars, planets, and even the very fabric of space itself. In the Big Rip, the expansion of the universe accelerates so rapidly that it overcomes all forces, gravity, electromagnetism, and even the strong nuclear force that holds atoms together. In the final moments, everything will be torn apart. The Big Rip represents the most dramatic end for the universe, one where not only matter but the very laws of physics are destroyed. The universe would end in chaos, with nothing left but empty space. The fate of the universe remains one of the greatest questions in modern science. Will the universe fade away into darkness? Will it collapse back into a singularity? Or will it be torn apart in a violent Big Rip? The answers lie in understanding dark energy, dark matter, and the fundamental forces that govern the cosmos. Ongoing studies of the universe's expansion, including missions like the Dark Energy Survey and the James Webb Space Telescope, may help us unlock the mysteries of dark energy and the future of the universe. As we continue to explore the universe and deepen our understanding of its forces, we move closer to discovering the ultimate fate of everything. Whether it's a slow freeze, a violent rip, or a dramatic collapse, one thing is certain: the universe, like everything in it, is not eternal. We may not know exactly how the universe will end, but we do know that every star, every galaxy, and even time itself has a finite existence. As we gaze into the night sky, we are witnessing the slow evolution of the cosmos, a journey that will one day reach its end. Whether it's a quiet fade, a violent collapse, or something beyond our imagination, the universe's story is far from over. The story of a neutron star begins with the death of a massive star. When a star that is at least 8 times the mass of our Sun reaches the end of its life, it can no longer generate the energy needed to support itself against gravity. Its core collapses under its own weight, and in the blink of an eye, a supernova explosion erupts, sending the star's outer layers into space. A neutron star forms when the core of a massive star collapses, squeezing protons and electrons together to form neutrons. This process leaves behind a small, incredibly dense core made almost entirely of neutrons. Neutron stars are typically around 20 kilometers in diameter, about the size of a city, but contain more mass than the Sun. This makes them the densest known objects in the universe, aside from black holes. Despite their small size, neutron stars are incredibly massive. A neutron star's density is so extreme that just a teaspoon of its material would weigh around 6 billion tons, the equivalent of all the buildings on Earth combined. Neutron stars pack their mass into a tiny volume, leading to a gravitational pull that is about 2 billion times stronger than Earth's. This means that if you were to stand on the surface of a neutron star, if it were even possible, you would be crushed instantly by the immense gravity. The gravitational pull of a neutron star is so strong that it can bend light around itself, creating a phenomenon called gravitational lensing. This warping of space-time means that we can see light from objects behind the neutron star, making the star appear as though it's surrounded by a halo of distorted light. When a massive star collapses into a neutron star, it begins to spin at incredible speeds. This rapid rotation is due to the conservation of angular momentum, much like a figure skater spinning faster as they pull their arms in. The result? Some neutron stars rotate hundreds of times per second. These rapidly spinning neutron stars are known as pulsars. As they rotate, they emit beams of electromagnetic radiation from their magnetic poles. If these beams happen to point toward Earth, we observe them as pulsing signals of radiation, like a cosmic lighthouse flashing in the night. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. Initially, these regular pulses of radiation were so mysterious that astronomers jokingly referred to them as signals from extraterrestrial civilizations. Pulsars are some of the most precise clocks in the universe. Their regular pulses of radiation can be timed down to the millisecond, making them incredibly useful tools for studying space-time and even detecting gravitational waves. Not all neutron stars are created equal. Some neutron stars possess magnetic fields so powerful that they can distort atoms and rip matter apart from thousands of kilometers away. These are magnetars, the most magnetic objects in the universe. Magnetars have magnetic fields that are up to 1,000 trillion times stronger than Earth's magnetic field. This makes them capable of emitting powerful bursts of radiation, known as starquakes, where the magnetic field violently rearranges itself. Magnetars are rare and short-lived. Their intense magnetic fields decay over time, and within about 10,000 years they quiet down, becoming regular neutron stars. While magnetars are rare, they are responsible for some of the most energetic phenomena in the universe, including gamma-ray bursts, blasts of energy so powerful that they can outshine entire galaxies for a few moments. Neutron stars are not only remarkable on their own, but they also produce some of the most dramatic events in the universe when they collide. When two neutron stars orbit each other, they gradually spiral inward, losing energy through the emission of gravitational waves. Eventually they collide, releasing an enormous amount of energy. When two neutron stars collide, the event releases gravitational waves, ripples in space-time that travel across the universe. In 2017, scientists detected gravitational waves from a neutron star merger for the first time, confirming decades of predictions. Neutron star mergers are also responsible for creating some of the universe's heaviest elements, such as gold and platinum. The collision produces a kilonova, a bright explosion that generates these heavy elements and scatters them across the universe. The gold in your jewelry or the platinum in your electronics was likely forged in the violent collision of two neutron stars billions of years ago. These cosmic collisions play a crucial role in enriching the universe with the elements needed for life and planets. The interior of a neutron star is one of the most extreme environments in the universe, and it challenges our understanding of physics. At the surface, the crust of a neutron star is incredibly hard, with densities far greater than anything on Earth. But as we move deeper, the conditions become even stranger. Beneath the crust, neutron stars may contain superfluid and superconducting layers, where matter behaves in ways that defy everyday experience. These states of matter allow neutrons to flow without resistance, and they could have a profound effect on the star's rotation and magnetic field. At the core of a neutron star, densities are so extreme that even neutrons may break down into quarks, creating a sea of subatomic particles. However, what happens inside a neutron star's core remains one of the great unsolved mysteries of astrophysics. Studying neutron stars allows scientists to test the limits of physics, including theories about the behavior of matter at incredibly high densities and temperatures. Neutron stars are some of the most extraordinary objects in the universe, born from the death of massive stars, yet more powerful and mysterious than we can imagine. From their incredible density to their rapid spin, from magnetic fields that warp matter to the cosmic fireworks they create when they collide, neutron stars push the boundaries of physics and continue to surprise us. As we explore these cosmic giants, we are reminded that even in the vast emptiness of space, there are wonders waiting to be discovered. Rogue planets are planets that do not orbit a star. Instead, they drift through the galaxy, traveling endlessly through the cold void of space. Unlike the planets in our solar system, which are anchored to the sun's gravity, rogue planets have no such ties. They are cosmic wanderers. Scientists estimate that there could be as many as 100 billion rogue planets in our galaxy alone, potentially outnumbering the stars themselves. These planets could be similar to Earth or Jupiter, or they might be something entirely different. Some may be rocky and barren, others could be gas giants with swirling storms, and some may have atmospheres thick with clouds. But how do these planets end up wandering through space? Rogue planets are believed to form just like regular planets, around stars in young solar systems. However, powerful gravitational interactions between planets can lead to chaos. A close encounter with a massive planet, like a gas giant or a nearby star, can send a planet hurtling out of its solar system, ejecting it into interstellar space. Rogue planets are often ejected from their parent systems due to gravitational interactions with other planets or stars. In the early stages of a solar system's formation, these gravitational encounters can be violent, leading to the expulsion of planets. Once ejected, the planet becomes a rogue, destined to drift through the galaxy. Without the warmth of a star, these planets plunge into darkness, cut off from their original system. Rogue planets exist in one of the most hostile environments imaginable, the cold, dark expanse of interstellar space. Without the heat of a star, these planets are plunged into eternal night, where temperatures can drop to unimaginably low levels. Temperatures on rogue planets can reach as low as 200 degrees Celsius. Without sunlight to warm their surfaces, most of these planets are likely covered in ice, their atmospheres, if they have any, frozen solid. However, not all rogue planets are cold and lifeless. Some may generate internal heat from radioactive decay or the gravitational friction of a molten core. This heat could keep parts of the planet warm, allowing for the possibility of liquid water beneath the surface. One of the most intriguing questions about rogue planets is whether they could harbor life. While life as we know it depends on sunlight, rogue planets could have other sources of energy. Internal heat from radioactive decay or geothermal activity could provide enough warmth to sustain life, even in the absence of a star. And some scientists believe that rogue planets could have subsurface oceans, vast bodies of liquid water hidden beneath layers of ice. If these planets have the right chemical conditions, they could potentially host microbial life. If rogue planets do have liquid water and internal heat, they might resemble the icy moons of our solar system, like Europa or Enceladus, where life could exist in deep oceans beneath frozen surfaces. Detecting rogue planets is an enormous challenge. Unlike planets that orbit stars, rogue planets don't emit light or reflect it. They are invisible to traditional telescopes, but scientists have developed ways to detect these hidden worlds. One of the most effective methods for detecting rogue planets is called gravitational microlensing. When a rogue planet passes in front of a distant star, its gravity bends the star's light, creating a temporary brightening effect that can be detected by astronomers. The first rogue planet discovered through microlensing was detected in 2011. Since then, astronomers have found several more, and they believe there could be billions of rogue planets yet to be discovered. Gravitational microlensing offers us a glimpse of these hidden planets, But many rogue worlds remain out of reach, drifting undetected through the galaxy. While rogue planets drift alone, they don't always remain isolated. As they move through the galaxy, they occasionally pass near other stars or solar systems. In some cases, these encounters could disrupt other planetary systems or even result in the capture of the rogue planet by a new star. If a rogue planet passes close enough to a star, it could be captured into a new orbit, becoming part of a new solar system. These encounters could also result in gravitational disturbances, altering the orbits of other planets or even triggering the ejection of other planets, creating more rogue worlds. Rogue planets are not only fascinating objects, they could play an important role in shaping the structure of the galaxy, influencing the formation and evolution of planetary systems through their gravitational encounters. As technology advances, our ability to detect and study rogue planets will continue to improve. Future space missions, such as the Nancy Grace Roman Space Telescope, are designed to detect more rogue planets through microlensing, potentially revealing thousands of these hidden worlds. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will have the ability to detect rogue planets smaller than Earth, providing us with unprecedented insights into the population of these orphaned worlds. As we discover more rogue planets, we will gain a deeper understanding of how planetary systems form and evolve. These orphaned worlds offer a unique glimpse into the chaos of the universe, where even the most isolated objects play a role in shaping the cosmos. Rogue planets are the lonely wanderers of the universe, planets without stars, drifting endlessly through space. While they may seem isolated, these orphaned worlds are part of the grand cosmic dance that shapes galaxies and planets alike. As we continue to explore the mysteries of the universe, rogue planets remind us that even in the cold darkness of space, there are wonders waiting to be discovered. In the vastness of space, where darkness stretches for billions of light years, there are rare, powerful objects that outshine entire galaxies. These are the brightest objects in the universe, cosmic beacons that illuminate the fabric of space-time with unimaginable energy. Let's start with the kings of brightness, quasars. These are the most luminous objects in the universe, powered by supermassive black holes at the centers of galaxies. As material falls into the black hole's accretion disk, it heats up to millions of degrees, producing an intense glow that can be seen billions of light years away. Quasars can emit more light than an entire galaxy, despite being concentrated in a region only a few light days across. They are powered by black holes with masses ranging from millions to billions of times the mass of the Sun. Quasars are found in the early universe, formed during a time when galaxies were still growing and merging. The most distant quasars are over 13 billion light-years away, meaning that we are seeing them as they appeared just a few 100 million years after the Big Bang. The light from the most distant quasar, Jota 33 in 1806, took 13 billion years to reach us. This quasar is powered by a black hole with a mass of 1.6 billion suns, making it one of the most powerful objects in the universe. If quasars are the steady beacons of the universe, gamma-ray bursts are its flashbulbs, sudden violent explosions that release more energy in a few seconds than the sun will produce in its entire lifetime. These are the most powerful explosions known to science. Gamma-ray bursts are thought to occur when massive stars collapse into black holes or neutron stars, producing jets of radiation that travel at nearly the speed of light. These jets shoot out from the poles of the collapsing star, creating an intense burst of gamma rays. Gamma-ray bursts can last anywhere from a few milliseconds to several minutes. Long-duration bursts are believed to be caused by the death of massive stars, while short-duration bursts may be the result of neutron star mergers. The energy released by a gamma-ray burst is truly mind-boggling. In just a few seconds, a single burst can release more energy than our sun will emit over 10 billion years. If a gamma-ray burst were to occur close to Earth, it could strip away our planet's atmosphere in an instant. Supernovae are the dramatic deaths of massive stars, explosions so powerful that they can briefly outshine an entire galaxy. These stellar deaths are not only visually spectacular, but they also play a crucial role in the universe, spreading heavy elements into space and seeding future generations of stars and planets. Supernovae occur when a star at least 8 times the mass of the Sun runs out of nuclear fuel. Without the energy needed to counteract gravity, the star's core collapses, triggering a massive explosion that ejects the star's outer layers into space. There are two main types of supernovae: Type 2 supernovae, which occur when a massive star collapses, and Type Ia supernovae, which occur in binary systems when a white dwarf star accumulates enough material from its companion star to trigger a runaway nuclear reaction. Supernovae are responsible for creating many of the heavy elements found in the universe, including iron, nickel, and gold. These elements are ejected into space during the explosion, enriching the interstellar medium and providing the building blocks for future stars, planets, and even life itself. For stars that are much more massive than our Sun, their deaths are even more explosive. Hypernovae are rare, but they are up to 10 times more powerful than regular supernova, releasing immense amounts of energy into the cosmos. Hypernovae are thought to occur when a star with a mass at least 30 times greater than the Sun collapses, forming a black hole. The explosion produces both gamma-ray bursts and supernova-like ejecta, making it one of the most energetic events in the universe. The most famous hypernova occurred in 1998, when astronomers observed a powerful explosion in a galaxy 120 million light-years away. This hypernova, SN 1998 BW, is believed to be linked to a gamma-ray burst, marking the first time these two phenomena were observed together. Luminous blue variables are some of the most massive and unstable stars in the universe. These stars are on the verge of collapse, constantly shedding mass and releasing bursts of light as they approach the end of their lives. They are unpredictable, chaotic, and some of the brightest stars in the sky. Luminous blue variables, like the famous star Eta Carinae, can undergo sudden increases in brightness, becoming hundreds of thousands of times brighter than the Sun in just a matter of days. These outbursts occur as the star ejects massive amounts of material into space. Eta Carinae, located 7,500 light-years away, is one of the most massive stars known. It has more than 100 times the mass of the Sun and is expected to end its life in a massive supernova or even a hypernova in the near future. These massive stars are living on borrowed time. Their violent outbursts are a sign that their cores are becoming unstable, and when they finally collapse, they will produce one of the most powerful explosions the universe has ever seen. In recent years, astronomers have discovered a new class of explosions known as superluminous supernovae, events up to 100 times brighter than ordinary supernovae. These rare, incredibly powerful explosions defy our understanding of how stars die. Superluminous supernovae are thought to occur when the core of a massive star collapses to form a magnetar, a type of neutron star with an extremely powerful magnetic field. The energy released by the magnetar powers the supernova, producing an explosion far more luminous than normal. The first superluminous supernova was discovered in 2007, and since then, several more have been observed. These events are so bright that they can be seen in galaxies billions of light-years away. Superluminous supernovae are the most powerful stellar explosions known to science, and they represent one of the greatest mysteries in astrophysics. As we continue to study these events, we may unlock new insights into the lives and deaths of the most massive stars. How far can we see? The night sky may seem infinite, but there's a limit to how much of the universe we can observe. The observable universe is the part of the universe we can see from Earth. Everything within a sphere centered around us, stretching roughly 93 billion light-years across. It contains all the stars, galaxies, and cosmic phenomena that have sent light or other signals to Earth during the 13.8 billion years since the Big Bang. The observable universe is limited by the speed of light. Since light travels at a finite speed, about 299,792 kilometers per second, we can only see objects whose light has had time to reach us. Anything beyond that is beyond our ability to observe. As we look deeper into space, we are also looking further back in time. The light from the most distant galaxies has taken billions of years to reach us, meaning we are seeing these galaxies as they were billions of years ago, long before Earth even existed. As we look farther out into space, we approach the edge of the observable universe, where galaxies appear as they were shortly after the Big Bang. These ancient galaxies are faint and distant, their light stretched and redshifted by the expansion of the universe. The most distant galaxy ever observed, GNZ11, is about 13.4 billion light-years away, meaning we see it as it was just 400 million years after the Big Bang. Beyond these distant galaxies lies the cosmic microwave background, the oldest light in the universe. This faint glow, first emitted when the universe was just 380,000 years old, marks the farthest we can see in terms of light. It is the afterglow of the Big Bang, a snapshot of the universe when it was still in its infancy. The cosmic microwave background was discovered in 1965 by Arno Penzias and Robert Wilson. It is the most distant source of light we can observe, and it provides a crucial piece of evidence for the Big Bang theory. One of the key phenomena that allows us to study the far reaches of the universe is redshift. As the universe expands, galaxies move away from us, and the light they emit is stretched. This causes the light to shift toward the red end of the spectrum, making distant galaxies appear redder than they actually are. Redshift is a result of the Doppler effect, where the wavelength of light stretches as the source moves away from the observer. The farther a galaxy is, the more its light is redshifted, allowing astronomers to measure its distance. By measuring the redshift of galaxies, scientists can determine how fast they are moving away from us and how far they are from Earth. This helps us map the structure of the universe and understand how it has evolved over time. The universe is constantly expanding. Space itself is stretching, carrying galaxies farther apart from each other. This expansion is a key reason why the observable universe has a limit. As space expands, distant galaxies move away from us faster than the speed of light, and eventually their light will never reach us. The expansion of the universe was first discovered by astronomer Edwin Hubble in 1929. His observations showed that galaxies are moving away from us, and the farther away they are, the faster they are receding. This discovery led to the idea that the universe had a beginning, the Big Bang. As space expands, galaxies get farther apart, and over billions of years, the universe has grown immensely. The edge of the observable universe represents the farthest light that has had time to reach us, but beyond that, the universe continues to expand. The observable universe is limited by the speed of light. But what lies beyond it? While we can't see past the cosmic horizon, scientists believe that the universe extends far beyond the observable sphere, perhaps infinitely. The cosmic horizon is the boundary beyond which light has not had enough time to reach us since the beginning of the universe. Anything beyond this horizon is invisible to us, but that doesn't mean it doesn't exist. As the universe continues to expand, more and more galaxies will cross this horizon and become invisible to us. In the distant future, the observable universe will shrink as the expansion carries distant galaxies beyond our reach. Eventually, only the closest galaxies will remain visible. As the universe expands, the observable universe will change. Distant galaxies will continue to move away from us, eventually crossing the cosmic horizon and disappearing from view. In billions of years, the night sky will look very different from today, with fewer galaxies visible and the universe appearing emptier. If the expansion of the universe continues to accelerate, as it is driven by dark energy, the observable universe will shrink as more galaxies move beyond the cosmic horizon. One day, only the galaxies within our local group will remain visible. The observable universe is not just a limit on how far we can see, it's a snapshot of a universe in motion, constantly expanding and evolving. As we look deeper into space, we are witnessing the universe's history unfold, but also glimpsing a future where much of that history will fade into darkness. The observable universe is our window to the cosmos, a glimpse into the past, present, and future of the universe. While we are limited by the speed of light and the expansion of space, what we can see is already vast beyond imagination. Beyond the observable horizon, the universe continues, perhaps infinitely. As we continue to study the cosmos, we come closer to understanding the true scale of existence, but the mysteries of what lies beyond will always remain just out of reach. Why does the universe exist? It's one of the oldest and most profound questions humanity has ever asked. For everything we see, stars, galaxies, planets, and life itself, There had to be an imbalance in the earliest moments of the universe. In the beginning, the universe was a hot, dense soup of energy, particles, and antiparticles. For every particle of matter that formed, there was an equal particle of antimatter, its mirror opposite. When matter and antimatter collide, they annihilate each other, converting into pure energy. Matter and antimatter are identical in mass but opposite in charge. For example, an electron has a negatively charged counterpart, called a positron, and a proton has a positively charged counterpart, called an antiproton. According to theory, the Big Bang should have created equal amounts of matter and antimatter. If that had been the case, the universe we see today, filled with stars, planets, and galaxies, shouldn't exist. All matter should have annihilated with antimatter, leaving behind nothing but energy. But that's not what happened. As the universe cooled after the Big Bang, somehow there was a tiny imbalance, a fraction more matter than antimatter. This imbalance, known as the baryon asymmetry, allowed some matter to survive, eventually forming the stars, galaxies, and planets that make up the universe. Scientists estimate that for every billion pairs of matter and antimatter particles, there was just one extra particle of matter left over after the universe cooled. It's this tiny excess that formed everything we see today. The baryon asymmetry problem asks why this imbalance occurred at all. Why was there more matter than antimatter? It's one of the greatest unsolved mysteries in cosmology, a question that could unlock new physics and a deeper understanding of the universe. One potential clue to solving the baryon asymmetry problem lies in a phenomenon known as CP violation. In particle physics, CP stands for charge parity symmetry. This symmetry implies that the laws of physics should treat matter and antimatter in the same way, except for their charges. In the 1960s, scientists discovered that this symmetry is not perfect. In certain conditions, particles and their antiparticles behave slightly differently, decaying at different rates or interacting differently with other particles. This violation of CP symmetry could help explain why there was more matter than antimatter in the early universe. CP violation was first observed in 1964 in an experiment with kaons, a type of subatomic particle. Later experiments with B mesons further confirmed that CP violation occurs, providing a key piece of the puzzle. Although CP violation has been observed, it's not enough to fully explain the baryon asymmetry. The difference it creates is too small to account for the imbalance we see in the universe today, meaning there must be other factors at play. In 1967, Soviet physicist Andrei Sakharov proposed a set of conditions that must be met to create an imbalance between matter and antimatter in the universe. These are known as the Sakharov conditions, and they form the framework for understanding baryon asymmetry. Sakharov's conditions state that for an asymmetry to form, three things must happen. There must be interactions that violate baryon number conservation, there must be CP violation, and there must be periods in the universe where thermal equilibrium is not maintained. The first condition, baryon number violation, refers to processes that change the number of baryons, particles like protons and neutrons. These interactions must favor matter over antimatter. The second condition, CP violation, is what breaks the symmetry between matter and antimatter. Finally, thermal equilibrium must be broken, meaning the universe must cool rapidly so that the imbalance is locked in before annihilation can occur. While CP violation has been observed, experiments have yet to confirm whether all the Sakharov conditions were met in the early universe. Understanding these processes may hold the key to explaining why the universe contains more matter than antimatter. Scientists are actively searching for answers to the baryon asymmetry problem through experiments that study the behavior of matter and antimatter. Particle accelerators like the Large Hadron Collider, LHC, allow researchers to recreate the high-energy conditions of the early universe and observe how matter and antimatter particles behave. At the LHC, protons are accelerated to near the speed of light and collided with each other, producing a shower of particles and antiparticles. By studying these collisions, scientists can measure CP violation and look for new physics that could explain the matter-antimatter imbalance. In addition to the LHC, other experiments are designed to measure the behavior of antimatter more precisely. For example, the ALPHA experiment at CERN traps antihydrogen atoms to study their properties and compare them to hydrogen. These experiments aim to uncover differences between matter and antimatter that might help explain why the universe exists as it does today. But despite decades of research, the mystery remains unsolved, and scientists continue to search for new clues. The standard model of particle physics has been incredibly successful in explaining the behavior of particles, but it doesn't fully account for the baryon asymmetry. To solve this problem, scientists are looking for new physics beyond the standard model, new particles, forces, or interactions that could explain why the universe contains more matter than antimatter. Theories like supersymmetry, which proposes the existence of partner particles for every particle in the standard model, could provide mechanisms for creating the matter-antimatter imbalance. Other theories suggest the existence of new forces or interactions that favor matter over antimatter. These new theories offer promising pathways to solving the baryon asymmetry problem, but they remain unproven. As experiments continue, scientists hope to uncover the missing pieces of the puzzle, potentially leading to a revolution in our understanding of the universe. The baryon asymmetry problem is more than just a scientific mystery. It's a question of existence itself. Why does anything exist at all? The answer lies in the earliest moments of the universe, in the tiny imbalance between matter and antimatter. While we may not yet have all the answers, each discovery brings us closer to understanding the fundamental nature of reality. As we continue to explore the universe, we are not only seeking to understand its past, but also the reason for its and our existence.